thinking about sets, consider what happens to the additive principle when the sets are not disjoint. Suppose we want to find A union B, and we know that the size of A is 10 and the size of B is 8. Well, if the two sets were disjoint, then we would say the size of A union B is 18, 10 plus 8. However, if they are not disjoint, meaning they overlap, we can't really tell what A union B is. This is not enough information. We do not know how many of the 8 elements in B are also elements of A. However, if we also know that A intersection B was 6, then we can say exactly how many elements are in A, and of those, how many are in B, and how many are not. 6 of the 10 elements are in B, so 4 are in A, but not in B. But that's me using words. Let's show a Venn diagram. Venn diagrams are always easier in this scenario, in these scenarios. So we have A and we have B here. Now we know that the intersection has size 6, and so the whole size of A is 10, meaning there's 4 left over for A. And then for B, this whole region, we know right here there are 6 elements, and so left over in B but not in A is 2. So that 6 plus 2 is 8, which is the size of B. All right, this says there are 6 elements in the intersection, 4 elements in A minus B, and 2 elements in B minus A. Now, these 3 sets are disjoint, specifically A minus B, B minus A, and A intersection B. Those 3 sets are disjoints, so we can use the additive principle to find the number of elements in A union B. It's just 6 plus 4 plus 2, which is, I can't do math, 12. This will always work, but drawing a Venn diagram is more than we need to do. In fact, it would be nice to relate this problem to the case where A and B are disjoint. Is there one rule we can make that works in either case? Well, here's another way to get the answer to this problem. Start by just adding the size of A and B. So start by adding these two right here. 10 plus 8, which is 18, which would be the answer if A intersection B was 0. We see that we are off by exactly 6 here. 18 is close to 12. But it's off by 6, which just so happens to be the size of A intersection B here. So perhaps we guess that A union B equals the size of A plus the size of B minus the size of A intersection B. This works for this one example. Will it always work? Well, think about what we're doing here. We want to know how many things are in either A or B or both. We can throw in everything in A and everything in B. This would give us the size of A plus the size of B, many elements. But of course, when you actually take the union, you do not repeat elements that are in both. So far, we have counted every element in A intersection B exactly twice when we count the size of A and the size of B. They overlap, and when you count them both, you're counting the middle twice. Once we put in the elements from A and once we included the elements from B, we correct by subtracting out the number of elements we have counted twice. So we added them in twice, subtracting once, leaving them counted only one time. In other words, we have a very important property here. I'm going to erase all this so we can see this main property, this main formula, more clearly. In other words, we have, let me make that a little larger. Come on. I can do this. We're almost getting to the climax of this video. Here we go. We'll leave it crooked. That's fine. There we go. For any finite sets A and B, A union B is the size of A plus the size of B minus the size of the intersection, because we double counted that intersection. Anyways, thank you so much, and I will see you in the next video.